A long-cherished dream of the Japanese people to connect the four main islands of Japan by a single unbroken railway network was finally realized with the opening of the Seikan undersea tunnel linking Honshu and Hokkaido beneath the Tsugaru Strait. Three tunnels were driven in this huge project. First, a pilot tunnel to gain advance information on geological and water seepage conditions along the main route, and at the same time to develop construction techniques to deal with the difficulties that would be faced. A service tunnel was also dug, parallel to the projected course of the main tunnel and separated from it by a distance of 30 meters. The pilot tunnel started from a depth of 120 meters, lower that is than the main tunnel, and was driven at a slight gradient of 3 in 1,000 to meet the service tunnel under the mid part of the strait. The service tunnel was driven ahead of the main tunnel and enabled detailed considerations of methods prior to starting excavation work on the main tunnel, and served for the transportation of personnel and machinery and the removal of muck. At 600 to 1,000 meter intervals along the service tunnel, connecting galleries were opened up to the line of the main tunnel, and from these, excavation of the dual-track Shinkansen-type main tunnel was carried out. The Seikan Tunnel, 53.85 kilometers in total length, of which 23.3 kilometers runs beneath the sea. Its cross-section is the same as that of Super Express Shinkansen dual-track tunnels. The tracks have a gentle minimum curve of 6,500 meters for compatibility with both Shinkansen and conventional rail traffic. They also have a gentle maximum gradient of 12 in 1,000. The tunnel traverses the strait 100 meters below the seabed. The most northerly points of Honshu are on the Shimokita Peninsula on the east side and the Tsugaru Peninsula on the west. Both were considered during studies of routes for the tunnel to Hokkaido. The conclusion reached was that while the distance between the cities of Aomori and Hakodate on the east route was practically the same, sea depths reached 250 meters, compared with 140 meters on the west route. Moreover, the east route would cut through a volcanic zone, which meant complicated, difficult strata. The west route between Cape Tappi and Cape Shirakami was therefore chosen for the basic survey. The survey of the seabed section began with dredging to obtain samples of rock. Drilling was conducted to gain a first-hand understanding of the geological structures beneath the seabed. Seismic, magnetic and sonic surveys were also carried out to assess indirectly the physical properties of the strata beneath the seabed. Results of these surveys were then confirmed by direct observation by means of a midget submarine. Dredging was conducted at 2,110 locations. Sonic surveys using sparkers were carried out over a total distance of 2,030 kilometers. It was decided that the only way to determine the technical feasibility of the tunnel would be to bore beneath the seabed and so obtain direct confirmation of the conditions there. Work therefore began on driving an incline shaft and the pilot tunnel as survey tunnels. Under the direct supervision of the Japan Railway Construction Public Corporation, tunneling began from Yoshioka in Hokkaido in May 1964, and then in 1966 from Tapi in Honshu. The work done in the survey tunnels included not only clarification of the geological conditions beneath the Tsugaru Strait, but also a range of tests to determine the appropriateness of excavation methods to be used, and the location of groundwater in the various kinds of rock and prevention of seepage. For the pilot tunnel from Yoshioka, a tunnel boring machine was used for faster work. But after the first 2,000 meters, rock conditions deteriorated and the machine could not. Six years after the survey tunnels had been begun, 4,100 meters of excavation data had been compiled, and the survey had reached a conclusive stage. It was known that the route of the tunnel passed through a complicated distribution of rock types. Neo-tertiary andesite, Kunnui strata composed mainly of tuff, Yagamo strata composed of hard shale, rhyolite, and the Kuromatsunai strata consisting of soft mudstone. And more than 10 zones of fracture were identified, cutting across the route, all producing considerable inflows of water. The water was found to be very similar to seawater. November 1971 marked an important event in the history of the Seikan Tunnel. The excavation of the main tunnel began at last. This diagram shows how excavation was carried out under the seabed. A pilot tunnel was driven to give advance indication of conditions that would be encountered. Grouting was employed to strengthen sections of soft bedrock and stop the influx of groundwater. And the method of using shotcrete and rock bolts together for support was adopted. These construction techniques were the basic methods adopted in the construction of the Seikan Tunnel and essential to its successful completion. As the pilot tunnel approached the midway point under the Tsugaru Strait, tunneling was a day-in, day-out battle against the influx of groundwater and geological obstacles. Because the Seikan Tunnel was being driven under the sea, there was always the possibility of sudden large eruptions of water with disastrous results. From the point of view of safety, therefore, pilot boring was carried out in the next section scheduled for excavation to determine geological conditions and to gain an accurate idea of the amount of groundwater to be expected. The horizontal pilot boring presented a particular difficulty, however. The shaft being excavated tended to drift deeper. The work did not therefore proceed as smoothly as had been planned. For this reason, research was carried out on long-distance horizontal boring in order to make it satisfy the necessary speed of the excavation work. A method to correct borehole drift was developed, as well as a double-pipe reverse boring method to permit excavation in adverse geological conditions. Excavation methods that brought great improvements in the length of boring sections were developed, and it became possible to obtain advance information on rock conditions up to 2,150 meters ahead. When advanced boring gave indication of groundwater or a zone of fracturing ahead, drilling was stopped and grouting carried out. Grouting, basically, is the injection of fluid grout into rock, in this case the walls of the tunnel. The grout penetrates the ground, and when it hardens it creates a grouting zone which prevents the inflow of groundwater and at the same time strengthens the rock. In the Seikan project, a considerable amount of research was carried out into grouting technology and developing materials, mainly to put a stop to the incursion of water. The LW method was adopted, using slag colloid, cement milk, and #1 water glass, which gives good penetration and excellent durability. Cement milk and water glass were fed separately into a pipe by grouting pumps, and at an intermediate point along the pipe they were mixed to form LW grout, which was injected into the rock. This illustrates standard grouting. Exploratory holes are drilled to ascertain rock conditions in the area about the section to be grouted and the presence of groundwater. First, second and third stage boreholes are then drilled. Finally, the effectiveness of the grouting is checked by means of check holes. The depth of grouting into the surrounding rock was 3 times the tunnel diameter. The effects of grouting appear at the working face. The red areas show where the LW grout has stabilized the rock. As excavation progressed, huge amounts of shotcrete were used as structural support material. The Seikan Tunnel was the first instance of shotcrete being successfully applied in this way in Japan. In the pilot tunnel, approximately 10,000 cubic meters of shotcrete was used. It proved to be an efficient and economical support material and a very effective method of stabilizing the surrounding rock. In sections where soft ground was liable to swell, rock bolts were used in combination with shotcrete to provide support for the tunnel walls. Here, work goes forward smoothly on the main tunnel section beneath the seabed. Men are hard at work at the tunneling face, everyone intent on his task. While methods were adopted according to the types of ground, the standard method was the side pilots heading and bench method. First, the side pilots were driven, then concrete was sprayed on the walls. Next, after excavating the heading or upper half, steel arch supports were set in place. After excavation had gone forward for about 150 meters, a 70-centimeter layer of concrete was sprayed onto the steel arch segments, and lining work was completed. In this way, the main tunnel with its dual Shinkansen track type cross-section was driven forward. Geological conditions in this particular section were difficult. Soft rock and ground swelling with a maximum ground pressure of a massive 200 tons per square meter. It took 4.5 years to construct an approximately 500-meter length of the tunnel here. The spring-silent method of excavation was used. A small cross-section drift is excavated on each side and the walls reinforced and improved prior to main tunnel excavation. This is the safest possible method. On May 6, 1976, however, during excavation work, a large inflow of water occurred at the 4,588-meter point in the Yoshioka section of the service tunnel, which was flooded. Maximum instantaneous inflow was estimated at 70 tons per minute. The next morning, incoming water under pressure flowed from the service tunnel through number 5 connecting gallery and into the main tunnel. This abnormally large influx of water was much greater than on any of the 3 previous occasions. It continued to pour in until it was exhausted at a constant rate of 16 tons per minute. Discharging the flood water was a very difficult task. After 70 days of tremendous efforts, the massive flooding was brought under control, restoration work began and normal working then resumed. This was possible because although the amount of incoming water was large, the quantity of soil it carried was a relatively small 1,000 cubic meters. Another factor was the calm and efficient steps taken by the engineering staff. They were well prepared by the research they had done on excavation techniques for use under adverse conditions. As the Seikan Tunnel was driven beneath the Tsugaru Strait from both sides, errors in direction had to be kept to an absolute minimum. Relative positions on both the Honshu and Hokkaido sides were therefore ascertained very accurately, and triangulation was carried out across the sea in just the same way as on land. As the tunneling went forward, measurement and survey work was carried out continuously inside the tunnel to ensure construction was proceeding as planned. January 27, 1983. The day finally arrived for the meeting of the pilot tunnels being driven from either side. From south to north, from Honshu to Hokkaido, for the very first time, wind was blowing uninterrupted from one island to the other without crossing water. Looking back at the start of the work on the incline shaft in 1964, 19 years had passed. 19 years of struggling against inrushing water and fractured zones. As the last wall of earth was pierced, the toil and efforts of the long project were forgotten. The world's longest undersea tunnel had finally come into being. The long journey had finally passed its most difficult stage. There was only 33 1/3 kilometers left for completion of the main Seikan Tunnel. Energy and skills were applied with redoubled vigor. In the main tunnel in the Tappi section, 13 kilometers from the Honshu side, excavation using the side pilots, heading and bench method had reached the final leg of the heading work face. And in January 1985, on the Hokkaido side, in the Yoshioka main tunnel, the final heading work face was reached. Excavation proceeded at full speed, toward the moment of hole through. On March 10, 1985, the world's longest undersea tunnel, the Seikan, joined Hokkaido with Honshu below the Tsugaru Strait. For the second time, a wind blows through the length of a passage beneath the strait, from Honshu to Hokkaido. There are large installations in the tunnel at both its Tapi and Yoshioka ends called emergency stops, where if the impossible should happen and a train catch fire, trains can be halted, their passengers evacuated under guidance, and the fire dealt with. Each emergency stop is 480 meters long and is provided with one evacuation passage for every 2 carriages of a train. These lead into the service tunnel, from where passengers go to an evacuation area. The possibility of earthquakes is always in mind, and constant observation is maintained by instruments installed inside and outside the tunnel. On March 13, 1988, the Tsugaru Strait route was opened to scheduled traffic. A new Seikan age had begun. 46 years have already passed since the Kanmon Tunnel linked Honshu to Kyushu in 1942. With the addition of the Seikan Tunnel, a land route joins the islands of Kyushu, Honshu, and finally Hokkaido. Japan has now a railroad backbone. The Japanese islands have been consolidated under a single, large-capacity railroad line that is safe, reliable, and unaffected by the weather. The first passenger train runs through the tunnel. And as the first train leaves the tunnel carrying new hopes and dreams, the old Tsugaru Strait ferry defiantly sets out on its last sea crossing, leaving behind countless dramas that have filled its 80-year history. Its last wake dying as it passes. As one ends, so the other begins. The Seikan Tunnel, the world's longest, joins the 2 sides of the Tsugaru Strait. The blood and sweat, the struggles and achievements of those who staked their all on this huge monument will long be remembered.